Welcome students. Today we are going to discuss about Riemer-Tiemann reaction. So in Riemer-Tiemann reaction we are going to first see which organic compound shows the Riemer-Tiemann reaction, what product we get out of Riemer-Tiemann reaction, what is the application of it, and what is the reaction, and finally we will see what is the mechanism involved in the Riemer-Tiemann reaction, and we will also discuss some other synthetic utility of Riemer-Tiemann reaction. So let us start. Riemer-Tiemann reaction. Which organic compound shows Riemer-Tiemann reaction? Yes, it is shown by phenols. Phenols show Riemer-Tiemann reaction, and it involves the introduction of CHO group. It involves the introduction of CHO group into this ring system, and the CHO group is introduced at the ortho position. So the product that you get out of a Riemer-Tiemann reaction is orthohydroxybenzaldehyde. What is it? Orthohydroxybenzaldehyde. Okay, so it is also called as salicylaldehyde. Orthohydroxybenzaldehyde, and also called as salicylaldehyde. Okay, so that is the product that you get. Now if you closely look at this structure, what is this? This is nothing but a phenolic aldehyde. What is it? Phenolic aldehyde. So you can say that the Riemer-Tiemann reaction, it is used for the preparation of a phenolic aldehyde. It is used for the preparation of phenolic aldehyde. Okay, so that is the introduction. Which organic compound shows this reaction? Phenol. What happens? Aldehyde group is introduced at the ortho position, and what is the net output? You get a orthohydroxybenzaldehyde, also known as salicylaldehyde. If you closely look at the structure, what is it? A phenolic aldehyde. So therefore Riemer-Tiemann reaction is used in the preparation of a phenolic aldehyde. Now, how to make such a phenolic aldehyde using this reaction? For that we have to look into the reaction itself. Let us look what happens in the reaction. In this reaction there is of course phenol. Phenol reacts with chloroform in the presence of aqueous NaOH to give sodium salt of salicylaldehyde, which upon acid hydrolysis yields your compound of interest, which is orthohydroxybenzaldehyde, also called as salicylaldehyde. Let us see the reaction once again. Phenol reacts with chloroform in the presence of aqueous NaOH to give sodium salt of salicylaldehyde, which upon acid hydrolysis yields orthohydroxybenzaldehyde. Now this H3O plus, this acidic, you don't have to add it externally. Okay, this acid is formed in the reaction itself, so it is spontaneous. No need to add this acid from externally. Okay, this acid is formed in the reaction itself, and how it is getting formed we will see in the mechanism. Okay, let us now discuss the mechanism. I'm rubbing this also so that we get a better view. Mechanism. Just a single sentence defines the mechanism. The first you have to write nucleophilic addition of phenoxide ion to dichlorocarbylamine. That's it. This is the first sentence that you have to write as mechanism. It's a single sentence that describes the whole mechanism. Nucleophilic addition of phenoxide ion to dicarbylamine. So from this mechanism, it is evident that you need two things. Okay, for this, one, you need phenoxide ion. Okay, that will be formed because there is phenol and phenol is acidic. So phenoxide ion will be formed spontaneously. No need to do anything. And the second thing that you need is dichlorocarbylamine. Dichlorocarbylamine. So how this dichlorocarbylamine is formed, we will see it in the mechanism. Okay, the mechanism involves 3 steps. How many steps? 3 steps. Let us see the step number 1. Step 1. What has to be formed? Phenoxide ion will be formed spontaneously from phenol because phenol is acidic. That thing that is that is of interest is dichlorocarbylamine. So the first step is formation of dichlorocarbylamine. Dichlorocarbylamine. Let us see how it is formed. Okay, so dichlorocarbylamine, for this you take chloroform. Take this chloroform. Okay, and react it with what is in the reaction system other than that? Do you remember? Yes, aqueous NaOH. So I am going to write the OH minus out of the aqueous NaOH. Okay, this OH minus, now it takes the H. Okay, it takes the H with it. Okay, so when it takes the H, what would happen? Yes, it takes H without taking its electron. So 2 electrons, they lie here itself. Okay, now this condition is very unstable. Okay, there is supposed to be 4 electrons around carbon atom, but this is 1, 2, 3, 4, 5. So this is very unstable, and this carbon doesn't need an electron, only then it can be 4. So what would happen? This carbon is actually not interested in this chlorine. The chlorine would take its electron, and what you get is this, right? And the chlorine takes its electron. Chlorine is here. Note this chlorine. Take a note of this chlorine out of first step. Okay, we will see in the third step how this chlorine reacts. So take a note of this chlorine in first step, and take note of this also. This is dichlorocarbylamine. This has got, actually it has got 4 orbitals. One of its orbital is bonded to the orbital of chlorine 1. One of its orbital is bonded to chlorine 2. One of its orbital is having a lone pair of electron, and the other orbital, that is the main thing, the other orbital is actually empty. It is actually empty. So this acts as a nucleophilic source. Okay, this is actually positive, therefore. Okay, this acts as a nucleophilic source. It needs a pair of electron in its orbital, which phenoxide ion would give. Okay, that we will see in step 2. That is why the mechanism was nucleophilic addition of phenoxide ion. Okay, the phenoxide ion comes and adds. Okay, it gives the electron pair to it. Okay, because it's an empty orbital here. The electron that was here, it was given to Cl minus. So here it resulted in empty orbital. Now this empty orbital wants to a pair of electron, and that pair of electron it can get from the phenoxide ion. So phenoxide ion comes and attacks this. Okay, so we will see that in the second step. Now this is dichlorocarbylamine. We have formed dichlorocarbylamine. Okay, I hope it is clear. Now let us go to second step. Do you think the dichlorocarbylamine will sit idle? Never. Okay, it has a empty orbital which requires a lone pair of electron, and that lone pair of electron which requires a pair of electron, and it can get it from phenoxide. Let us see step number 2. Nucleophilic addition of phenoxide ion. Nucleophilic addition of phenoxide ion. phenoxide. Okay, let us see what happens now. You have the phenoxide ion. This is formed from phenol. No need to do anything. Phenol is acidic. Phenoxide ion will be formed spontaneously. And here we are using actually aqueous NaOH. There is a base already in the system. So the phenoxide ion will be formed at a faster pace and at a greater concentration. So no need to do anything. The phenoxide ion is actually formed. Now what can happen here is it can react with your dichlorocarbolamine. It has got its pair of electron, lone pair of electron when chlorine left, and it also has got a empty orbital. Okay, right? Okay, if you remember, it has got an empty orbital too. Now what would happen here? This would come here, right? This always jumps here. When this jumps here, the electron pair jumps here. It's a perfect condition for this to attack this. So nucleophilic addition takes place, and what would result? Let us see. So here we have got double bond O. Here one H is there. Actually all carbon have a hydrogen. We are taking out this one to better understand the mechanism of the reaction. And here we have got CCl2. The empty orbital has accepted the pair of electron from this position. Okay, the empty orbital has accepted the pair of electron from this position. Okay, so now what would happen? Now, do you remember that in the first step H2O was formed when chloroform reacted with OH minus took H, right? And CCl3 was formed, right? So when OH minus took H out of this, H2O was formed. You write that H2O here, H plus OH minus. Fine. Now what would happen is, actually this is very unstable situation in this benzene ring, because there are only 4 pi electron. So actually benzene is 6 pi electron. So it requires a pair of electrons. So this pair of electron goes here. When this pair of electron goes here, this pair of electron, the carbon here becomes 5, right, bonded to 5 atoms. So it is unstable condition. So this pair of electron jumps here. When this pair of electron jumps here, and this H plus which goes out, when this pair of electron comes here, that H plus, it comes here. Fine. And here, what is the role of this? This H plus actually requires a pair of electron, so it goes here. So I hope you got this. So now what we get is OH, right? And here we are getting CHCl2. CHCl2. I hope you got this. This is the most important to understand, that this is actually unstable, 4 pi electron, and this jumps. When this jumps, it is 6 pi electron. It becomes stable. The H plus goes. When this jumps here, this carbon becomes attached to 5 atoms. So that is unstable. So this jumps here. The H comes and attacks here, and this H plus comes here. So that's it. So this is the net output that we get. Now what would happen is, it would react with what is here remaining, OH minus. You write 2 OH minus. Okay, and take one H and react with one of the OH minus, and you will get H2O. Okay, still there is one more OH minus. Take O out and attach it here. Okay, and take this Cl2 out. Okay, so what you get? Let us see. O minus, because one of the H has gone to OH minus to give H2O. There is one more OH remaining. That O you write here. Take that Cl2 out. In that place you write an O. There was H here. Write this H. This Cl2 that goes out, okay, Cl2 goes out. Here there is one H which remains. See, H goes to one of the OH minus, one O goes here, there is one H left. That H reacts with Cl2 to give what? HCl. To give HCl. Now there is one chlorine also which is left, right? One chlorine also which is left. This chlorine plus reacts with chlorine minus that was formed in first step, if you remember. In first step, one chlorine went out from this, right? There were three chlorines. So one chlorine that went out from this, that comes and combines with this chlorine to form Cl2. So I hope you got everything, right? So now what is formed is HCl and H2O, that is the net output that is formed. So now the whole thing has become acidic. So initially when I started this, I said that you don't have to add acid from outside. The reaction itself will produce acid. So now it has produced an acid, right? We have got a salt of salicylaldehyde. In step 3, what would happen? Acid hydrolysis will happen because there is acid and water. So acid hydrolysis of salt of salicylaldehyde, acid hydrolysis of salt of salicylaldehyde. What would happen here? Yes, take out that thing from the second step. This was it, O minus and CHO, HCl and water is formed. It would generate H plus. Now that H plus will come and combine with OH, and here you go. You get the salicylaldehyde, orthohydroxy benzaldehyde, or you can say a phenolic aldehyde you have got. Dear students, Riemer-Tiemann reaction is used in the preparation of coumarins, catechol, benzofuran and salicyl dioxime, and these are the other synthetic utility of Riemer-Tiemann reaction. If you have understood the class and if you have liked the video, don't forget to subscribe the channel. Thank you very much.